Okay, so it's my great pleasure to welcome today Lisa Kewley to give us the seminar within Commission J1 of the International Astronomical Union. So Professor Kewley is the director of the Harvard-Smithsonian Center for Astrophysics in Boston in the United States. She got her PhD in 2002 from the Australian National University on the link between star formation and supermassive black holes, with postdoctoral work at the CFA, and then also as a Hubble Fellow at the Institute for Astronomy in Hawaii. Her expertise focuses on the role of star formation and AGN activity on galaxy formation and evolution, with emphasis on the gas physics as traced, for instance, by emission lines. And I encourage everybody to have a look at this really nice review of Lisa on 2019 in Annual Review of Astronomy and Astrophysics. It's actually a very nice reference to have a look at. She returned to Australia, continuing her research at ANU with a number of accolades. Many of them actually, so it's a long list here, but I just put a few. Being elected fellow of the Australian Academy of Science, she had a prestigious ARC Laureate Fellowship, and she was elected to the US National Academy of Sciences and the American Academy of Arts and Sciences. She led the Astro 3D initiative, which is a major actually research project that was extended to various institutions in Australia. And in 2022, she became the director of the Center for Astrophysics. And today, Lisa will be telling us about her work on modeling the UV to infrared emission line spectra of galaxies. So thank you very much, Lisa, and yeah, take it away. Thank you.
Thanks very much, Ignacio, for that warm welcome. Let me share my screen here and go to slideshow mode. Okay, you see that okay?
Yes, yep.
All right, great. Okay, so this is work that we've been doing over the previous few years, and we're now basically at the point where we're building a really big grid of 3D photoionization models that will be made available to the general community, and we're really excited to be at this stage of the project now. So I'm going to give you an overview of the whole program, and then where we're up to at the moment, and then the sorts of things that I'm excited about in terms of future instrumentation for modeling of the ISM and galaxies. And so just a quick summary of the talk. I'm going to give an overview of the models, and then I'm going to talk about the photoionization model inputs, some of the advantages and disadvantages of the models. I'm going to describe and show you some of the different photoionization models that we currently have, and then I'll describe our work towards the fully consistent H2 region ISM modeling. And then I'm going to talk about the applications of these next generation photoionization models that we're creating. Okay, so this is the way we were modeling emission line spectra. And the way we've still been going, for the most part, about modeling galaxy and H2 region spectra. So what we've been doing is we use a stellar evolution synthesis model, which the inputs into that are a stellar atmosphere model and stellar tracks. And then that model puts out an EUV ionizing radiation field, which is then used as an input into a photoionization model. And then we use a dust model as well with that. And then that produces a theoretical spectrum. It covers the full spectral range from the UV right through to the far infrared. In fact, it even goes further than the UV. It produces X-ray lines as well. Now, this looks pretty simple, but it's not really, because we actually have all these different parameters that we input into these models, including the IMF, the stellar population age, star formation history, metallicity, ionization parameter. We can either put in a density or pressure that controls the temperature of the nebula, and then we have a metallicity and geometry that we enter into the models as well. So I'm going to talk about some of these parameters and how we've been working towards more accurate, more reliable models over time. Okay, so the first model I'm going to talk about, let's see if I'm going to click here. Yeah, so the first part I'm going to talk about is the stellar evolution synthesis models and some of the main features of those models and things to take into account when we're using these models. So this is on the right here shows you the ionizing radiation field that we get out of a typical stellar evolution synthesis model. And it shows the ionizing spectra or the ionization potentials rather for different elements. And so, for example, the ionization potential for hydrogen, the first ionization potential is here, and shown here between gray and red. And so all the various ionization potentials for each of these elements are shown. And what this plot shows is that the different ionization potentials of the elements are very sensitive to the shape of the EUV spectrum, and in particular, this part of the EUV spectrum is highly uncertain. It's actually really dependent on the stellar atmosphere models. It's dependent on whether you have opacities and how you model the opacities in those models, as well as whether you have things like single stellar populations or binary stars, and they can all change the shape of the radiation field here. And in addition to that, the age, just the cluster age of the stellar population, which is shown in these different colors, can also change the shape here and whether you get a larger or smaller number of ionizing photons. This is in log space, so a small difference here is actually really a large difference in the actual number of ionizing photons. And so the EUV spectra depend critically on the stellar age, and they also depend critically on the metallicity. And so this plot now shows the different ionizing radiation fields, but for different metallicities. And you can see there's really a big difference right here. And this is in particular, it's going to impact things like the oxygen 3 line, it impacts helium 2, and then any other lines with ionization potentials, you know, in this region right here. And so there's many issues with that. That means that we have to know the metallicity of the stellar population before we model the H2 region of galaxy, and often we don't. Often we're actually using the models to derive a metallicity rather than tailoring the model to the object with a specific metallicity. And then different stellar tracks you can enter into the stellar population synthesis models. For standard optical emission lines and optical emission line diagnostics, the stellar tracks actually have very little effect on those optical diagnostics. So if we, for example, here, this is done by a former student of mine, Josh D'Agostino. If we compare these different stellar tracks here, and then you can see there's very little difference. And it's, you know, this is well within the errors of the models, the photoionization models themselves. And so we also compared stochastic versus non-stochastic IMF sampling as well. And there's larger differences, in particular down here at the higher metallicities, but overall, again, it's less than about 0.1 dex, which is the typical errors of those models. And so we're at least fortunate in that respect. But one of the things that have been concerning me over the past few years has been the abundance sets that we're using in our stellar evolution synthesis models. And so in the past, we were using Anderson-Graves sets. They're still the ones that are used in our metallicity diagnostics that we had produced prior to 2019. And so these abundance sets, when you actually compare them with observations, turns out that for some elemental abundance ratios, they're not actually very accurate. Now that we have more observations of H2 regions and stars in our Milky Way in our local neighborhood. So, for example, in the past, a uniform scaling was used. So for elements such as argon to oxygen, for example, or chlorine to oxygen, it was basically just a single scaling with abundance. So if we say we've got twice solar, we would multiply that abundance ratio by 2. And but that's not necessarily the case. You can see here for neon, so neon to oxygen, you can't just scale it. The neon to oxygen actually appears to be larger at higher metallicities than it would be at lower metallicities. So you'd actually want to be taking this scaling into account. For argon to oxygen looks all right. Also, the other thing to take into account is the is whether there's any offsets actually between the Anderson de Graves sets and observations. And so this figure on the right shows you the Anderson de Graves, what they assume for the chlorine to oxygen ratio, which is higher than the observations, and the fit later on, the fit by Lotters 2009 for these observations. We added our own H2 regions to this plot, shown in the blue here. And so David Nichols, this is some of the work that he did. He's still a postdoc for me at the Australian National University. And so he did a very careful job of looking at different H2 regions. He basically developed a large sample of H2 regions as well as the stellar abundances, put them all together and did fits of them to see whether they agreed with Anderson de Graves. We found that in many cases they did not. And so we've actually produced a new set of abundance scalings, and we call these the galactic concordance abundance sets. And this changes dramatically the temperature of the nebula, so how much abundances you assume of the elements, because elements act as coolants, they change the temperature of the nebula. We calculate the temperature at each distance, or at each step through the nebula. And so if you are changing the abundances, you change the temperatures, you're actually changing the emission lines that you would then produce because they are sensitive to the temperature. And so this shows the difference between if we had our galactic concordance non-uniform scaling with solar, where we allow the elements to scale up or down with solar according to the observations rather than having it flat. And so the red here is the non-uniform abundance scaling and black is the uniform. So you can see clearly that the non-uniform abundance scaling really does match the Sloan data better. These points up here are AGN, so we don't expect star-forming models, which are shown here in red and black, to fit those, but we do expect the models to fit the full star-forming galaxies in the SDSS here, which is what the non-uniform galactic concordance abundance set does. In addition, here on the right-hand side, we're showing also the Anderson-Graves uniform abundance sets here in green, and the various ones as well as the Anderson-Graves ones in blue. And again, they also have this sort of feature where it's not reproducing the full set of line ratios that we actually see in local star-forming galaxies. And so the problem now that means is that the stellar tracks in the stellar evolution synthesis models then had the older abundance sets in them. And even though we could update our photoionization models to use the galactic concordance abundance sets, they weren't consistent then with the stellar evolution synthesis models because the stellar tracks were using the old abundance sets. And so we set out to fix that problem. And this is work done and continuing to be done by Katie Grusher, who's at the Australian National University. She's done really excellent work on this, and she's a postdoc there. So here she derived new stellar tracks and new opacity tables for the galactic concordance abundances to be used in stellar evolutionary synthesis models. And so here's some examples of the luminosity temperature relation for different tracks. These are showing different metallicities in iron to hydrogen, and showing the galactic concordances in the solid lines, and then the ones with the Anderson-Graves abundances are in the dot dash lines. And so while there's really very little impact for regular abundances, once we get down to lower metallicities, then we start seeing these differences between the different tracks. We have some more differences shown down here. And then just to emphasize the importance of that, this here, let's see, shows, so on the left is the previous stellar tracks with the Anderson-Graves abundances. So these are the ionizing UV radiation fields produced with those tracks using the stellar evolution synthesis model. And on the right, if we do a zoom in, so we're now zooming in on a portion of this spectrum here, just where we're seeing these ionization potentials here. You can see the difference between these ones. And this is again with different stellar ages. So we now have predicted the UV radiation, and it does vary substantially. And again, looking at the ion to hydrogen ratio, but this time in terms of ionizing photons. And we're using different metallicities in terms of ion to hydrogen. You can see there's differences in the number of ionizing photons that we get when we're using the galactic concordance stellar tracks. And so this is work that Katie is continuing to work on at the moment. And so what she's now doing is she's using these stellar tracks in the stellar evolution synthesis models with mappings, photoionization models, to then make predictions for the chemical abundance ratios. And she's using hydrodynamic simulations, so doing a combination of the two to derive metallicity diagnostics across cosmic time that can be used across cosmic time that have self-consistent abundance sets. And so that work's ongoing. Okay, so now I'm going to talk about our work on photoionization modeling. I'm super excited about this work because we're really close to being able to have a full model grid for our new photoionization models. So some of the options that you have for photoionization models include mappings, which is the models that were developed by Ralph Sutherland and Mike Doppiter at the Australian National University, and that includes self-consistent treatment of nebular dust and shock physics. So you can apply them to H2 regions AGN and also regions shocked by supernova or galactic winds and jets. And then on the other hand, you also have cloudy. That also does a similarly detailed self-consistent treatment of nebular dust and molecular physics. They both include complex radiative transfer, photoionization, and dust physics for more than 30 elements. And in these models, both these models, the focus is on obtaining the correct nebular temperature and density in either 1D or 2D. In cloudy, it also includes photodissociation regions, and so is useful for producing molecular lines. And at the time, before we started doing our 3D Monte Carlo radiative transfer, there was some other options, including moccasin, which has been applied to H2 regions of various geometry, and then another one called CM MAPPINGS, which is a self-consistent Monte Carlo, and that's for H2 regions as well, surrounding young OB stars or other radiation fields. And again, that has a simple photoionization. They both had fairly simple photoionization, limited number of elements, and what we really wanted was to combine the two, in that we want to do Monte Carlo ray tracing. It's a more accurate thing to do because we know that photons travel through a nebula. We know we have different dust geometries and gas geometries, and we want to actually be taking that into account. But in the past, it's been computationally intensive to do that. And so we're finally at the point now with our supercomputers, and here we're using the Harvard supercomputer system, that we can actually do 3D Monte Carlo radiative transfer, but we can do it for 30 elements. So it's a very exciting time to be doing emission-line modeling. I just wanted to highlight before I talk about our models, some of the things. So mappings in cloudy really don't differ very much if you use the same input parameters. It's less than 0.1 dex on average. They do, I consider these models, for 2D or 1D radiative transfer, they really are state of the art. And they have significant advantages in that they do take temperature, ionization, pressure into account. So they change throughout the nebula. And you can apply them to H2 regions and galaxies as well as at high redshift, as long as you have appropriate input parameters, but I'm going to talk about that. The disadvantages are that as I said earlier, they're extremely sensitive to stellar atmosphere modeling. The dust depletion factors are often not well constrained, and the detailed codes, they are limited to spherical or plane parallel geometry, and that's historical, and it's because that's all we could compute with the computation time available. quick note about dust depletion factors. So we started observing H2 regions. Dust obviously impacts our observations substantially, and especially in H2 regions, nearby H2 regions. And we wanted to constrain the dust depletion factors better. And this is ongoing work being done by David Nichols at the Australian National University. And so what we did was we went out to the Siding Spring 2.5 meter telescope, the WIVES, to use the WIVES spectrograph, which was built by Mike Doppiter, shown in the right here. And we obtained what we call hyper-resolution spectra. So these are extremely high resolution spectra of local H2 regions. This is one for Orion Nebula, but we've got a range of other nebula as well. And so with these type of observations, every single line and wiggle here is actually a real line. It's not noise. So we can zoom in, for example, and even then, every single line here is a line. And so what that means is we've got thousands of lines. And so we're actually applying our models backwards. We're able, with Orion and with, in particular, we're looking at single star H2 regions. For those, we can constrain the ionizing radiation field really, really well. And then the depletion factors actually become free parameters. And so by having these very detailed spectra, we're able to fit for the depletion factors. And this is the work that's ongoing. It's actually really hard because a lot of these lines are produced by different processes. We need to make sure we're modeling them very accurately. Some of the ones that are very weak lines still need to be identified. And so it's an exciting project, but takes a long time. Now, the other thing that we've been working on, as I've been mentioning, is the geometry of the models. And so we were limited to spherical and plane parallel geometry. This has a lot of problems. And in addition, the H2 regions in the past has often, and are still the diagnostics we're often applying, have been assumed to have constant density and temperature. And so I'm just going to show you some reasons why we shouldn't be making these assumptions. So most models would assume a constant temperature or density, but if we allow the temperature and the density to vary through the nebula, so we fix the pressure rather instead, you can see that they actually do vary. So we've got radius or thickness of the model on the bottom, on the x-axis, and then we've got models for different metallicities here shown, and we've got the temperature here on the y-axis. And you can see that, there's very little models that would actually be a constant temperature, maybe here, this one or this one, and very few that would also be constant density. Most of them actually vary. And so the question is, are these models actually enough? We are now varying the temperature and we are allowing the density to vary through the nebula, but are these actually accurate? Do we get data that look like this? And when we compared with the data, and this is work being done by my former PhD student, Yifei Jin, now a postdoc at the Institute for Theory and Computation here at Harvard, what we find is that they don't really look like that. So, for example, this is just taking one line of sight through Orion, but you can take many lines of sight and you get this looks different. The temperature structure in Orion, and the red and the black are different ways of measuring the temperature using different lines. You actually get different temperature structure with radius. And then here's the density structure. And so it's not a single, slope. It actually, this particular one goes down and then up again. And so they're not usually constant in a nebula. They're certainly not constant across galaxies. And so we then went and used the WIVE spectrograph to observe single star H2 regions, and in the SMC and the LMC and our Milky Way, to look at the electron temperature and density maps. What do they look like? And so we also obtained emission-line maps, but this is one of them. This is the electron temperature maps that we measured using the oxygen 2 auroral lines, the nitrogen 2 and the oxygen 3 lines. And then the bottom are the density maps. And so the density is really clear. It's quite clumpy, and we have quite different temperature maps for these different elements. And so we can also look at different H2 regions and see how how they compare. And so these now are comparing 4 H2 regions, and we're looking at temperature in all of these figures, and you can see that the temperature for these different species. So again, we've got nitrogen 2, oxygen 2, and oxygen 3 measures of temperature. And there's some interesting geometries here that we see for temperature across the nebula, but nobody would be able to argue really that they're constant, that you have a constant temperature. And in fact, when we look at them, we compare the data with the models. The data are shown in the colored line. So this is sort of the range of temperatures and densities that we're observing. And compared with the models, which are shown in black, we're getting wildly different distributions from the models. So the models aren't accurate enough to be able to reproduce the temperature structure or the density structure that we were seeing for the H2 regions. And the problem is that we were assuming that H2 regions were spherical. And, you just have to look at them. Clearly, they're not spherical. Look at them. Sometimes they've got bipolar or blister-like geometries, and they could also can have shells and other structures here, biconical type structures like this one. And so we really need to actually take that into account. And so this is really the trigger for us to develop the new, as well as the computation advances that have been made in the last few years, to combine Monte Carlo radiative transfer with our mappings photoionization code so we can do arbitrary geometries. And so the geometry that we set in these models, we use log normal density distribution. These are basically fractal geometries. And this is an example of the type of geometry that we get in these H2 regions. If we take slices through this cube, we can actually see the geometry of the emission line. So H beta and oxygen 3 and nitrogen 2, these are slices through the various axes. And so they do have interesting and complex geometries, even in the resulting emission lines. And so we are doing the full photoionization model treatment. We've got the full radiative transfer and the cooling and heating for the 30 elements, but with the Monte Carlo radiative transfer of the photons, and we use photon packets. And so these are, some of the resulting H2 regions that we get compared to, they look more realistic compared to the real H2 regions. At the moment, we're doing fairly simple models. We're just, in our new grid that we're running now, we're doing a larger range of models. So for these ones here, we had a central ionizing star with effective temperature of 40 kilograms. But and an ISM abundance of solar radiation bounded, but we're now varying these parameters as well as density distribution, a parameter that can characterize the density distribution as well. And so we'll have a grid of models with different metallicities, with different ionizing stellar populations, and also different density distributions. And so this is work now. BFA has been publishing a series of papers on this. He's got 3 papers now. I really encourage you to read them if you're interested in this work, because we're having really interesting results. And so with the models, we first started looking at the impact on the emission line predictions that we were doing in the past and how they might differ with the new geometries. And so a point that I wanted to make is where these lines are being produced in the nebula. So in particular, when we have a nebula, in a spherical nebula, we're actually, some of these lines are produced in the outside part of the nebula, like oxygen 1 and sulfur 2 is generally produced more towards the outside, whereas lines like oxygen 3 and the hydrogen lines tend to be produced more towards the middle of the nebula, closer to the ionizing source. And I'm going to show you a plot that shows that from the models in the next slide. Well, the point that I want to make is that if you've got a line that's being produced in the outer parts of a nebula, when you compare a clumpy geometry like this and the type of ionization map you would get for these lines, you have a larger perimeter or a larger edge region over which you could produce the oxygen 1, for example. So you can produce it in here, in here, in here, in here, in here, compared to if you had a spherical model. And so there's some edge effects for edge elements, or we call them boundary species, that are produced near the boundary of the nebula. There's the larger zone in the clumpy geometry where they can be produced. And so in particular, if we look at these species, so you look at the different lines and where they're produced in the model. So oxygen 3, as you saw, was produced, fairly well spread out. But nitrogen 2 is produced more towards the edge, and sulfur 2 and oxygen 1 are primarily produced towards the edge of a nebula in a spherical or a plane parallel geometry. Now, in a clumpy geometry, the region and the boundary at which these are produced is much larger. You can produce them in these sort of fingers. And because they can be produced in a larger zone, then you actually get a larger flux in these lines. And so the oxygen 1 and the sulfur 2, when you compare the 3D models compared to our previous 1D models, you get a significantly larger amount of flux, even more than twice for O1, and more than about 1.5 times for sulfur 2. And so this is going to impact the predictions that we get for the sulfur 2 H alpha and O1 H alpha for those lines. And there's more minor impacts on the nitrogen 2 and oxygen 3. Those are going to have some impact on metallicity diagnostics. And so we need to take those into account as well. And so just to emphasize that fact, in these models, we've got a spherical model here. So in the outer region, this is where, you might get those boundary species being produced. But in this, the clumpy model, it can be produced all along here. And so this shows you the different line maps that we would get from these different lines. And this is R23 is a metallicity diagnostic, really very different geometry distribution. And even the ionization parameter, it's not simple with a clumpy geometry. And that's because there are lines of sight through the nebula. So you can get some lines of sight, lines of photons passing through clumps and then hitting clumps further out. They can still have a higher ionization parameter than they would in a spherical geometry. Okay, so if we then compare them directly, and so this is our fractal nebula, this is our equivalent spherical nebula. They look roughly, just on first glance, the same, but if we divide them by each other, so we've got our spherical nebula on the y-axis and our fractal nebula on the x-axis, then you can see the impact on these lines, the regular standard optical diagnostic lines here, when we're looking at the flux. Now we're integrating now over an entire H2 region. We're not looking at lines of sight. So the integrated flux is what we normally look at when we're looking at H2 regions. And so it's interesting that there's an impact on the O3 line. This is a key diagnostic line for metallicities when we do an integration over the whole nebula. And that's primarily due to the change in the ionization parameter and where oxygen 3 can be produced. Okay, and so now we're comparing the models with both models here on the BPT diagrams. We know that this, as I showed you in a plot earlier, the Sloan galaxies lie sort of along here like this. And so in our spherical equivalent model, we weren't usually able to accommodate all the full range of emission lines that were seen in the H2 regions, particularly for sulfur 2 H alpha and O1 and H alpha. But with our complex geometry, we can actually produce the gray shaded points here. We can reproduce the whole emission line abundance sequence and much larger range of line ratios, in particular for S2 and O1 than we were in the past. We always had trouble modeling S2 and O1 and being able to produce the full range of ratios that we observed, especially at the high end. So I'm mindful of time because I want to get to the what's next with these models. So this is where we're up to with our models at the moment and the latest papers on this. So we've been observing SMC, LMC, and Milky Way H2 regions, and then those went into determining our new dust depletion factors, which are complete and are now in the models. as well as geometry, investigating different geometries and producing the new 3D Monte Carlo code. We developed the concordance abundance sets and put them into the new stellar tracks, which then went into the stellar atmosphere models and the stellar evolution synthesis models, and allowed us to produce the new 3D photoionization model in a self-consistent way with self-consistent abundance sets. And so what's next for the models is we want to do new self-consistent diagnostics, but we also want to do AGN. I'm going to give you a sneak preview of our work on AGN. And then we want to publish our new dust attenuation factors, and we're also then planning on developing diagnostics in order to do a more consistent measurement of the star formation and metallicity history of galaxies using more realistic models. And so this is just a sneak preview of some work that my grad student here at Harvard, Pei-Shin Su, is working on. And she did this work at the Australian National University. It's now published. And she's been working on metallicity diagnostics for AGN. And so in the past, when we were doing mass metallicity relations, we're throwing away the AGN. We basically take the star-forming galaxies and apply star-forming metallicity diagnostics. But you actually want to, when you're doing mass metallicity relations, you ought to be including the galaxies with AGN as well. They also sometimes have star formation in them. And so she's been developing new diagnostics in the optical and UV for AGN. This is an example of some of them. N2H alpha is a strong diagnostic, as is N3 on O3. And then there's some various other good quality diagnostics as well. The colored curves show you different ionization parameters, and we have also different pressures in here as well in the different lines. This figure shows you some of the other diagnostics. Is that the same one? That's the same one. Here's another one. So we're also producing diagnostics in the IR. And the IR, there's a larger dependency for some diagnostics on the ionization parameter and pressure. What we really love is this one, neon 3 on bracket gamma. This is beautiful. It's got basically, very little dependence on ionization parameter and pressure, and that's a sort of makes an ideal diagnostic. Neon 2 on silicon 2 is also quite a good diagnostic, but you need to have a handle on the the pressure here. Okay, so I'm super excited by James Webb. We have wonderful data, so I expect that these diagnostics and the new models will be excellent for applying to James Webb data. Really beautiful emission lines we're getting now at very high redshift, and I think it's fair to say that it's really changed how we do science now. It's changed our idea of what high redshift is and what intermediate redshift is, and so we're super excited to start applying our new diagnostics to James Webb data, and our team in particular is involved in the SEERS program that is being led by Stephen Finkelstein. We're also really super excited by the ELTs coming online. I know that the European ELT is going to come online in 2029. A really exciting time for astronomy and groundbreaking discoveries. Here at the CFA, we're a partner in the GMT. And we're building here at the CFA multiple instruments for the GMT, but it includes instrument suite includes the first light imager spectrograph called GMAX, which is aiming to take spectra of galaxies at the epoch of reionization and resolve galaxies, and also do sort of workhorse spectroscopy. And this is going to be really excellent for these type of diagnostics in the future at the optical and infrared regime. Another instrument that's a second generation instrument for GMT is called GMTIFS, and this is a near-infrared adaptive optics driven integral field spectrograph. And so we did some simulations for what type of, what we would get for emission line maps using GMTIFS. And so this is the type of resolution we would get for a Z of 1.5 galaxy using GMTIFS. And what this means is that the types of work we're doing right now with nearby H2 regions, where we can actually, have a look at temperatures across them, or we can look at how the temperatures or the metallicities vary across all the H2 regions within a galaxy, asymmetries, for example, we'll be able to do it intermediate redshift. So at redshift of 1.5 to possibly even up to 3 for some galaxies is going to be super exciting. So really looking forward to that. At the moment, for measuring spectral energy distributions of galaxies and also chemical elements in galaxies, Chandra is really critical. It's the highest resolution X-ray observatory. This is an observatory that we're operating here at the CFA. It's under risk at the moment because in the President's federal FY25 federal budget proposal, Chandra is slated to have a $20 million budget cut this year and then another $20 million budget cut in the coming couple of years, which would cause Chandra to close out and we would have to close it if the budget continues to be that way, because we wouldn't be able to operate in anymore. It'd still be functioning, still fully functional telescope. So that would be a tragedy where we're hoping that doesn't end up being enacted by Congress. But I just wanted to make that point that it's actually really critical to maintain our X-ray capabilities because it is fundamental for a lot of our spectral energy distribution and whether we know there's an AGN in galaxies or not. And it's very important for our emission line diagnostics to know whether there's an AGN or what is the relative ratio of AGN and star formation when we're applying our AGN and star formation diagnostics. I'm also really excited by Athena-X and to be launched by ESA. It's been delayed, so I think the last I heard was maybe that it's going to be launched in the 2030s. If anybody knows, please correct me if I'm wrong. But I'm super excited by this, and Athena-X is going to turn me into an X-ray astronomer, I think, because it's going to be able to do temperature and metallicity and density in galaxies and galaxy clusters for all these elements that we don't have access to in the optical, UV, or infrared. And so, for example, we'll be able to do abundances here for magnesium, for silicon, iron, sodium, aluminium, all these things. And so it's going to be very exciting. That'll help us constrain AGB and supernova yields. That'll help to refine chemical evolution models. We'll be able to do chemical history of clusters in multiple of these elements. And so it's going to be really exciting, and hopefully that it maintains its capabilities and that it goes up sooner rather than later, because I'm very excited by that. Okay, so I think I'm running out of time, so I just wanted to end by saying that the next generation photoionization model is coming. We're currently running a big grid. Yafei is going to be publishing the big grid in his upcoming paper, and it'll be available for anybody to use, primarily at the moment for H2 regions, and then in future also for galaxies. So thank you very much.
Okay, thank you very much, Lisa. Great talk. So, are there any questions? Please, you can actually, yeah, Nick, actually, you can, please go ahead.
I was simply clapping hands.
Ah, okay, sorry.
Very nice talk, Lisa. Thank you.
Thank you, Nick.
Very nice.
So anybody, if you want, raise your hand, or you can actually just open the mic and ask. I mean, in the meantime, one question I had, Lisa, in the first part of your talk, you were mentioning about the really important aspect to know that the abundance ratios that we have it's basically crucial in order to be able to translate the emission lines into a proper estimation of the properties of the ISM. So I'm just wondering, I mean, you're referring to this, you have this galactic concordance. So now what happens if you're considering other types of galaxies? For instance, very massive galaxies may have undergone very different star formation histories, possibly different chemical enrichment histories. What do you make of that for the analysis of?
Yeah, so actually that's some work that Katie Grash has been doing. She would like to develop an abundance set specifically for high redshift galaxies. Some of them we think may be enriched in nitrogen, for example. So it'd be nice to do a nitrogen enriched set. And so this is a capability that we have now to be able to do. And yeah, absolutely, that's on our agenda, and Katie's leading that.
So do you have some sort of a feeling as to what would be this conundrum that we have at high redshift with the nitrogen abundances? I mean, what could be causing that? What's your feeling?
I guess I'm in two minds about it. It may be that there are different nitrogen abundances at high redshift. It's just that the lines that we're using currently to measure the nitrogen abundances can be impacted by other things. So for me, I'm kind of on the fence about it because you can have higher ionization parameters. So you could have, for example, more stars per unit area producing the same effect. You could have a higher pressure producing the same effect. It may be that the geometry is producing an effect. You might have contribution from galactic winds, shocks from galactic winds. If there's an AGN contribution, there's all sorts of things that could increase your nitrogen lines relative to the lines that they're being compared with, oxygen or H alpha. So I just think, or even sulfur too. So I just think that we just have to be really careful. And what I'd love to be able to do, in future, and this is with the ELTs, I think, is to be able to do a more robust measurement of the nitrogen in galaxies. But that's going to wait, I think.
Right. I mean, connected to this in a way, because it shows the big difference. I mean, normally, for instance, people that are simply users of these diagnostic diagrams, like BPT diagram, and you say, okay, my point is here, it's going to be a star forming system, it's going to be an AGN. So one question I have is also, there is now all this hot topic that has become very interesting, which is the presence of AGN in dwarf galaxies.
Absolutely.
And there's some work that has been done with IFU data. And sometimes you see very strange things, that you see the stuff going outside and you have a lot of work on basically saying, be careful with the shocks that could be actually having an effect and it could be misinterpreted. So could you tell us a bit about this?
Yeah, absolutely. So in the dwarf galaxies, and in fact, that's something that a new student that's coming here, Sophia, wants to work on, is to have a look at IFU data of dwarf galaxies, especially ones with and without AGN, so control samples. Certainly, if you have a dwarf galaxy, the low metallicities are going to completely change where they lie on things like the BPT diagram. So they'll mimic a low metallicity star-forming galaxy, even if they have an AGN in them. And then the impact of shocks on that. So what's unfortunate is that for low metallicity galaxies, the AGN model grids on a BPT diagram like this go straight with metallicity, straight across horizontal, but so do the shock models. And so for low metallicity, so low metallicity takes everything in that direction where the low metallicity dwarf galaxies, star-forming galaxies lie. So everything tends to, cluster in the one region. And so you can't use those diagrams anymore. But my student Pei Xin has been working on 3D diagnostics that they also use velocity dispersion and sometimes distance to also help separate this. And she says and she's writing a paper on it at the moment, where it seems to be that you can get 3 forks in a 3D diagram between star formation, AGN, and shocks. And you can actually see this when you rotate it around. They form these different forks. And so you can see the star forming sequence, and it lies where the models do. It's really remarkable. But you need the third parameter, because you just can't use the regular 2D diagrams to do that separation. And it's true that in dwarf galaxies, the crossing time is very short, so that they can be very impacted by galactic winds, for example, and they can have quite different, they don't have abundance gradients necessarily, and so they can also have pockets of very low metallicity if another galaxy is quickly fallen in an even smaller galaxy. You can see these sometimes. They're very interesting. So you really want to have, I agree with doing it with IFU data for sure. But you need high resolution IFU data, high spectral resolution in order to get the velocities. And most of the IFU observations that's being done at the moment with the big surveys, they actually don't have enough resolution to be able to make these 3D diagrams. We're using now Muse is good, and we're also using a sample called Typhoon to make these 3D diagrams, but we're probably going to have to go out and get our own observations that's high enough spectral resolution for dwarfs.
And in principle, I guess that on top of the velocity dispersion or the shape, is it because sometimes I have seen some papers where they show potential AGN activity in regions that would be relatively outside, so not so much centrally located. So would you simply be very skeptical, or could you say that there still could be AGN related?
Yeah, so I mean, we do see it in a regular star-forming galaxy, with an AGN in it. So you've got star formation in it there as well as AGN. We do see extended AGN narrow line regions going out, and it can be many kiloparsecs. Right? And it can be past 12 kiloparsecs. It can be quite far. So it depends on how big the dwarf galaxy is, but you could do that, but you could also get exactly the same line ratios from a wind.
Right.
And you tend to see the shock line ratios from winds in the outskirts, because that's the only place you can see it. You might have shocks through the whole galaxy, but it's usually that those lines are dominated and contaminated by the star formation, or if there's an AGN, those tend to dominate. And the only place you can see the shock dominate is in the outskirts. And so every time I see, strong N2H alpha or S2H alpha in the outskirts of a galaxy, I get skeptical, because you think it's probably shocks. But the way to tell is by velocity dispersion. So shocks produce very specific velocity dispersions, which are related to the shock velocity. Might be 500 kilometers per second or 300 kilometers per second. You can't produce that from H2 regions, and it's unlikely that far from that AGN to be able to produce that from an AGN. But so you can use a velocity dispersion that way.
Right. Yeah, there's a question. Please go ahead.
Hi, Lisa. Really nice talk. So I have a comment about what was previously said, that in the BPT, in the optical BPT, like diagrams, you cannot distinguish between AGN and H2 region like galaxies. If you use UV diagnostics, you may be able to separate them, but of course you don't always have the res frame UV. But that's just a comment. My question is, SDSS 5 local volume mapper has started taking data, so that's an IFU survey. It doesn't have the spatial resolution you need for your 3D models, if I understood correctly, because it has a spatial resolution of 36 arcsecond. The fibers are pretty large. However, it's getting a complete IFU survey of the Magellanic Clouds and the southern Milky Way. So have you thought about synergies between having, many individual H2 regions like SDSS is going to get, but which you cannot, for each H2 region, you cannot produce a 3D map, and doing very detailed, but, fewer sample.
So we are looking at what we can do with lower resolution. So we are, we can deconvolve our spectrum, so we can actually just make it coarser. So with the high resolution models, we can make them coarse resolution, or we can integrate over some area, and we can integrate over. We can basically simulate, the data that you would get with other surveys. It's something that Patience just started looking at. So she's been simulating what you would get if you had a single aperture, right? And can you still use the 3D diagnostics in that way, or at what resolution will it fall apart, and what resolution, what's the lowest resolution, spatial resolution you would need, or what's the lowest spectral resolution you would need? So that certainly is something that we're looking at, because absolutely we know that it's, the perfect resolution, it kind of doesn't really exist, compared to the models. So but that is absolutely on our radar, and I can't wait for those IFU data to come available. It's gonna be awesome.
Thank you.
Yes, there's a question. Elias?
Hello, Dr. Kewley. Thank you very much for the very nice talk. I have a maybe naive question about the AGN metallicity diagnostics that you showed in the end of the talk. My understanding so far is that we use the metallicity on the star-forming galaxies because we can measure them. But I'm not sure how you can use the emission lines that you showed in the, for example, the H alpha, flux, because in the AGN the excitation mechanism would be different, right, than the
Yeah.
star forming
So we're using
galaxies.
AGN. We're using AGN power models.
So the sample of the galaxies on which you measure the H alpha flux, for example, is a AGN sample.
Yes, so we have an AGN sample, and we also have AGN ionizing radiation field. We don't use the starburst models to produce AGN diagnostics.
Because I thought of
yeah.
because I thought of it as a global model, as a global diagnostic, so you can use every galaxy.
No, they're not global. So yeah, you have to use the star forming models and the star formation diagnostics for star forming regions, and then the AGN model and the AGN model diagnostics for AGN regions, and you can't combine them really. We are looking at ways of separating and to try to work out what spaxels in IFU data would be AGN and what fraction, and we can do a reasonable job of separating them. Rebecca Davies has a series of papers with IFU data where she uses the IFU data and actually is able to separate between star formation and AGN and calculate for every single line and every spaxel what the percentage contribution is from the AGN compared to the star formation. We use a combination of data and models to do that. And then she compares, for example, the O3 luminosity with the X-ray, hard X-ray luminosity, or the H alpha star formation rate with the infrared star formation rate. And they match quite well. It's actually quite remarkable. I was really surprised that it works quite well. And so now we're looking at these 3D diagnostics in order to do that. Because with galaxies, you've got often have a combination of the two.
Yeah. And if I may, a follow-up question about the diagnostic. Is there any new diagnostic that could separate in the way that BPTs, the BPT diagrams do, the AGN from the low luminosity AGN? Because when you work with star-forming galaxies, as in my case, a problem is how to separate star-forming galaxies from low luminosity AGN.
Yeah.
And I'd like to know if there is any new diagnostic that we are working on.
Yeah, so low luminosity AGN, so they tend to fall in the liner region of the spectrum, in the liner region of those diagnostic diagrams. But what I still recommend for those is to use the sulfur 2 diagram and the O1 diagram, not the N2 diagram, because they can lie in the composite or just in the star forming part of the N2 diagram. So don't use that diagram. And then we have tried to, what we'd like to do, ideally, you'd like to be able to model the ionizing radiation field in those low luminosity AGNs, and in order to be able to predict where they lie on that diagram or different diagrams. So we have been looking at a range of different diagrams to try to, we've looked at it all in the UV and infrared, which we've been trying to find a diagram that clearly separates them out from the other AGN, the regular AGN, or from shocks or from old stellar populations, which can mimic those on a BPT diagram. Right. And it's not that clean. It's really really hard. There's always some sort of degeneracy. We tried really a lot, and you get excited by a diagram, and then you throw some shock models on there, and then it's like, oh, that's not very good.
Yeah. Okay, thank you very much.
Thank you.
Any other final question for Lisa?
Yes. I wanted to make a comment. Oops, sorry. Yes, I wanted to make a comment. Lisa, in the last several years now, I have not been working on galaxies anymore. So that's why we did not bump into each other in a conference. So I now work exclusively in high energy astrophysics. So we don't see each other at conferences. So the only thing I wanted to say is that you have made major progress since the last talk I heard from you.
Thank you. Appreciate
several
that. Thank
years
you very
ago.
much.
Congratulations.
Thank
You've
you.
done very well. Yes.
Thank you. I really appreciate that.
Okay, so I might take just a chair's privilege to ask just one final question. I cannot help because it's so much interesting stuff here. So just your comments, what do you think on because basically when you go in the details, you realize how complicated it is. I mean, using a simple diagnostic, a single emission line ratio, everything could be interpreted in a simplistic way. So what is this connection that, for instance, we try to constrain the initial mass function of star-forming galaxies by looking at ratios between some emission lines? And how sure are we that, yeah, don't. Okay, that's the answer.
Oh, no.
I mean, there have been, as you know, these claims that, for instance, in some dwarf galaxies, there were some ratios between some lines, and it could be interpreted as this or that type of IMF.
Please don't do that.
Okay, that's good to hear. That's good to hear. Okay, thanks so much, Lisa. So yeah, I mean, really fantastic talk. It was really nice, and we'll post this on YouTube so that many people can enjoy this one. So thanks so much. Oh, I think there's a final question, Elias. No, it's a clap. I still.
Yeah, I'm clapping.
Okay, great. So Lisa, thanks so much, and
Thank you.
thanks for your time. And as I said, we will post this in YouTube, and I very much hope that many people will be listening to this really interesting
Thanks
stuff.
very much. And thanks,
right.
Sarah, for your comment in the chat. Bye.
All right, take care.
Bye.
Bye-bye.
Bye.